So welcome back to our course, to the 6th lecture. I hope you enjoyed your work on probabilistic programming. Today we learn about some selected methods of explainable AI. So for more details, please refer to the course webpage and look up the syllabus. We are now in week 19, slightly delayed but still on course. Okay, agenda for today, reflection as usual. Then some definitions on explainability, interpretability, causability, and so on. We will then answer the question, is XA new? XA is short for explainable artificial intelligence. Then we will learn some examples for Ante-hoc models. And then we go deeper into examples for post-hoc models. That means making the black box model interpretable. And here we will deal particularly with some selected methods, for example, local interpretable model agnostic explanations, LIME. Then beta, black box explanation through transparent approximations, LRB, layer-wise relevance propagation. Here we take also the next assignment. Then we will deal a little bit with Taylor series, then prediction difference analysis, and finally we conclude with testing with concept activation vectors, TCAV. Okay, reflection. As first, the usual reflection. So what do you see here? Yes, correct. This is a factored probabilistic graphical model. So this is very useful for inference and learning, as you can remember. So we learned 3 different types: undirected random Markov random fields, for example, used in computer vision, or directed graphical models, for example, for designing models. And these factor graphical models, they define the relationships between the variables in the graph. So as you can see here, each factor can be connected to many other variables and comes with a factor function to define the relationship between these variables. So factor graphs are very useful in the medical domain because they are often used in protein networks. And you can remember proteins are the building blocks of life, so they are everywhere in the medical science. So what do you see here? Yes, this is the joint probability distribution of theta given the data. And learning usually means computing a maximum of the parameters given the data. You can remember this was the argmax. And now the logical next question is, how do we express that in a graphical way? So this is then question number 3. How do we express that in a graphical way? Right, this is done via the so-called plate notation. So important to note is that here we assume that the data is IID, independent, identically distributed. And this assumption is shown in the notation here. So the data points X are conditionally independent given theta. And it is at the same but repeated X sub I node. So this box here is called plate, and the large letter N, so the capital N, specifies the number of repetitions of the X sub I node here. Okay, finally, because it is so important, please explain the differences between deduction, induction, and abduction. Yes, deduction, the conclusion follows from general premises, and in deduction the truth of the conclusion is guaranteed by the truth of the statements or facts considered. Correct. Then induction, this is forming a generalization based on what is known or on the observed data. So for us now interesting is to add probability, so probabilistic induction, for example. And we have given some examples last time. And abduction finally is to create an explanation. Okay, so let's start. So there are some definitions we should make clear. So remember, this is part of explainability. we need a mutual understanding, and this requires to define exactly what we mean with something. Otherwise, we have misunderstandings or misrepresentations. Okay, so the first question is, why is explainability so important? So explainability is now en vogue, as you know, although it is maybe the oldest field of mankind. So every little child is asking these questions of why. And since humans exist, there are questions of why. And for example, I can ask now, why are you studying machine learning for health informatics? So let us quickly summarize, and we will learn more, of course, during this lecture. So explainability is motivated by the opaqueness of so-called black box machine learning approaches. We will deal with this later on. It is the ability to provide an explanation on why a machine decision has been reached. That means, why is a cat when the deep network recognized the cat? And here a note, finding an appropriate explanation is very difficult because this needs an understanding of the context. This is very difficult, and it needs a providing of a description of causality and consequences of a given fact. We will see that later on. So just for the sake of completeness, in German Erklärbarkeit, auch Verstehbarkeit, Nachvollziehbarkeit, Zurückverfolgbarkeit und Transparenz. Okay, then explainability often argued would interpretability be a better term? And yes, up to a certain point. Cynthia Rudin from Duke University comes up and argues that we should not use the term explainability, but instead interpretability. I agree. But it is meanwhile explainability or explainable AI is meanwhile an accepted term. So it is difficult to get rid of this term. But later on we will deal with it. So interpretability is the ability to explain or to provide the meaning in understandable terms to a human. And now you see the human comes into play. So explainability, interpretability is inherently including a human. We explain something to a human. Okay, and understandability, also intelligibility. This is the characteristic of a model to make a human understand its function, how the model works without any need for explaining its internal structure. And there is a third term, comprehensibility. This would be the ability of a learning algorithm to represent its learned knowledge in a human understandable fashion entities. So you see, we always refer to a human, so we have the human here. And to be honest, I think XI is a good name because it is already well known and can, similar to AI and ML and deep learning, used as a top level name. So for example, interpretable machine learning is technically what we would like to enable, and the top level view is explainable AI. And because real explaining, for example, giving visual explanations in plain language is very difficult, but we will come to this back later on. So you can still remember the famous Judea Pearl from the enormously successful probabilistic graphical models. So Judea Pearl received the Turing Award. This is the Computer Science Nobel Prize in 2011 for his work. And he has written a nice book. I recommend that you read it. It is the book of why, and the key of science is causality. So the question of why, as children are doing from the very beginning. So if you take time, you can also listen to this beautiful interview led by Lex Friedman with Judea Pearl. So causality is really very, very important, and you see it in the next slide. Causality is the art and science of cause and effect. So causality is the effectiveness that connects the cause, in German Ursache, with the effect, in German Wirkung. And causality is the relationship between one process or state to another process or state, and this is a fundamental principle of all natural sciences. Yet, I would say it is science per se. So in classical physics, an effect cannot occur before its cause, of course, and philosophically it means all effects must have a particular cause. So this is really very important in the medical domain and for us in the medical sciences. And we have worked on a different concept, and the concept as causability. So we introduced causability, and you see causability. So in contrast to causality here and causability here. So causability is the measurable extent to which an explanation, for example, received from explainable AI methods, for example, from a heat map, of a statement to a user achieves a specific level of causal understanding. So with effectiveness, efficiency and satisfaction in a specified context of use. And the context of use, this is the very important aspect. So basically, causability can be defined as mapping machine explanations with human understanding. And we have chosen this term causability in reference to the word usability to make it clear. And I will elaborate a little bit on causability. So the first question is, what is the difference between explainability and causability? So in explainability, this is the technical sense. In the technical sense, this highlights decision-relevant parts of the used representations of machine learning algorithms and the active parts in the algorithmic model, so that either contribute to the model accuracy on the training set or to a specific prediction for one particular observation. So this is purely technical. This is explainable AI, and it does not refer to an explicit human model. Okay, so this is really very important, this definition. And causability, as we have heard before, is the extent to which an explanation of a statement to a human expert achieves a specified level of causal understanding with effectiveness, efficiency and satisfaction in the specified context of use. So you quickly realize now the big difference, and it will make sense to you why this new concept of causability is so important, particularly for the medical domain. So on the one hand, it is to measure the quality of explanation, and on the other hand, as the fundament to build future human AI interfaces. And this we will urgently need in the future medical AI world. If we want to bring AI or machine learning or however you call it into clinical routine, we need drastically new interface concepts to ensure this explainability, understandability, retraceability, and this for legal, social and ethical reasons. So there is no debate of this necessity. And here, a very old image of myself, so to answer slightly the question of how we can build successful future human AI interfaces. So explainability, you see clearly, is the part of the machine of computer science. Causability is the part of the human. And only if we ensure 100% mapping, then we have 100% good explanation. So ideally, future interfaces will enable a medical expert to state questions and ask, for example, for counterfactuals. That is this what would be if. Counterfactuals are very important. They consist of the what if and if I had only and so on, and that occurs when thinking of how things could have turned out differently. So counterfactual thoughts include things that in the present and now could never happen in reality because they solely pertain to events that have already occurred in the past. And such counterfactuals can provide totally new insights into science and, of course, in the medical sciences. So, How can we measure the quality of explanations? We need measurements, and we have developed the system's causability scale. And I will explain what it is. So metrics of AI, system causability scale, in short SCS. SCS is not for Shopping City Süd. So this is for systems causability scale. And let's explain it to you, and remember this SCS will become very important in the future. And we have recently, so this is relatively recently defined it. So if we look at this picture, first let us define. So a statement S, for example here, a statement S can either be made of a human, this is subscript H, so S sub H, or can be made by a machine, so S sub M. Whereas S is a function of R, K, and C, and R is a representation of an unknown or unobserved fact, U sub E, related to an entity. So this is the entity here. And K is the pre-existing or the previous knowledge, which is for a machine embedded within an algorithm, for example in a knowledge graph, or made up for human by explicit, implicit, and tacit knowledge. Remember back to our lecture on data, information, and knowledge. We have different types of knowledge. And C is the context. So for a machine, for example, the technical runtime environment, and for humans, the physical environment, so where the decision was made. This is the clinical environment, for example, the medical environment where the medical person is making the decision. So we call it pragmatic dimension. And now an unknown here, an unknown or unobserved fact, U sub E, represents a ground truth GD that we try to model both with machines M sub M or as humans M sub H, human machines. Okay, so maybe I should note unobserved, hidden or latent variables are found in the literature for Bayesian models, for example, for hidden Markov models and methods like probabilistic latent component analysis. So, however, the overall goal is that a statement is congruent with the ground truth, and the explanation of a statement highlights applied parts of the model. Okay, so what problems do we face in the real medical world? So I cannot often enough ask you this question, and this is maybe the problem we are faced besides of confronted with the non-IID data. I think I have already mentioned it, but I repeat it. So ground truth is not always well defined, especially when making a medical diagnosis. Although human scientific models are often based on understanding causal mechanisms, today's successful machine models or algorithms are typically based on correlation or related concept of similarity and distance. And you know, correlation is not causation. So mapping, I come back to mapping, is really very good, and also ground truth is a very well defined term. So the term itself comes historically from cartography. So in remote sensing, ground truth refers to information collected on location. So this is really what it is down on the Earth's surface, okay? And therefore I like the term mapping, because we have done our job if the ground truth is mapped 100% on the model. So the real Earth surface versus the cartography map. Okay, and ground truth allows image data, for example, to be related to real features and materials on the ground. So the collection of ground truth data enables calibration of remote sensing data and aids in the interpretation and analysis of what is being sensed. So I've mentioned context often. Very important is to know what is the context of the explaining, and this we will discuss in the next. This is, to my opinion, very important. At first, we always need to define what we want to have explained, to whom, and in which way, how. And this is central and particular in the medical diagnosis. So, but for us engineers, do we want a mechanistic understanding or a functional understanding? And if functional, what do we want to explain? For example, do we want to interpret a predicted class or explaining individual decisions? So we should always know it in advance what we want to achieve. This is very important, so please remember this. And this is true, of course, for medical diagnosis. And here I have a nice starting example from machine learning-based tumor infiltrating lymphocytes. This is short TIL evaluation, so tumor infiltrating lymphocytes. And here on the far left in the picture in the slide, you see this original H&E breast cancer image. So H&A is short for hematoxylin and eosin. And in the center now, you see the machine learning based classification scoring of regions with respect to their lymphocyte content. So green here means no lymphocytes, and red means, of course, a high content of lymphocytes. And on the far right, we see now a heat map, and the heat map explains the classifier decisions with pixel-wise resolution and demonstrates how lymphocytes are identified and localized. So this heat map is generated by a method we will get to know later on. This is called layer-wise relevance propagation, LRP. So you will see this later. By the way, lymphocytes counts can be derived from the heat map as well, or directly during the classification. So blue to green means no evidence of lymphocytes, yellow to red means increasing evidence of lymphocytes. Yeah, of course you will now ask, what is a lymphocyte? So a lymphocyte is one of the subtypes of a white blood cell in a vertebrate's immune system. Lymphocytes include natural killer cells, so this function is cell-mediated, cytotoxic innate immunity. There are T cells for cell-mediated cytotoxic adaptive immunity, and B cells for humoral antibody-driven adaptive immunity. So they are main type, and the cells are found in the lymph, and therefore the name is lymphocyte. Okay, this was just a digression. So DARPA did a really good job because they initiated the XI program and they coined the term explainable AI and started therefore to rethink back to the early AI days when people still used and understood their models. So, however, this image is problematic because you must see it in a different context. This was intended to make you aware that the best performing methods are at least transparent, but in no way explainability can be correlated with performance. So please be careful. This is far too naive. Explainability, or here better interpretability, does not correlate with performance, has nothing to do with it. So please be careful. So how is explainability, interpretability contrasted then to performance? This is a nice picture image from Zachary Chase Lipton, who works on algorithmic fairness. And he shows that typically evaluation metrics require only predictions and ground truth labels. So when stakeholders additionally demand interpretability, this can be very difficult, really difficult, because we might infer the existence of underlying factors which cannot be captured and which do not show and which do not come out at all. So please remember what I told you in the beginning. Start with the question of what, how, and to whom you want to explain it. So please be aware of that. Okay, so what are then human-friendly explanations? What are personalized explanations? So explanation must be seen as a reasoning process. And now a few open questions. These seem trivial maybe, but they are very difficult to answer. For example, what is a good explanation? Or when is it enough, the degree of saturation, for example? Or context dependent, so emergency, for example, if you have very few time to make a decision versus research, where you also have not indefinite time, for example, in cancer research. And then how can we measure the degree of comprehensibility and a given explanation of a given explanation? Here we have the system causability scale, SCS. Yeah, obviously this is obviously the explanation was good when it has been understood by the human. When you not know, then you have understood it. So what can the system learn from the human? This is also very important, but not trivial. But what can the human learn from the system? And you see, this is a really, really good task for human-computer interaction. And of course, measuring explanation effectiveness. Was it effective? So what are then the main expectations of this field of XA? XA is now in every corner. So there are of course huge expectations towards the field of XA. Yeah, causality, of course, inferring causal relationships from pure observational data in the sense of Judea-Pearl. Then transferability, so humans have a much higher capacity to generalize, and they can also transfer learned skill to completely new situations. Then informativeness, for example, a diagnosis model might provide intuition to a human decision maker by pointing to similar cases in support of a diagnostic decision. Okay. And then fairness and ethical decision making, so interpretations for the purpose of assessing whether and to what extent decisions produced automatically by algorithms conform to ethical standards, very important in the future. And maybe the most important is trusted AI, that means interpretability as a prerequisite for trust. And this was first asked by Ribeiro et al. How is trust defined? Is it by confidence and so on? And we will look at this later on. So for now, what is interpretable models versus interpreting models? So we have the interpretable glass box models. That means that the model itself is already interpretable. For example, regression or naive Bayes, random forest, decision trees, for example, graphs. Graphs are already interpretable also to a human. Yeah. And then we have these interpreting black box models. So the model is not interpretable and needs a post-hoc interpretability method, for example, via decomposition, line beta, LRB, and so on. So we will go into detail later. So, but here now just that you have a top-level overview on these two families, interpretable versus interpreting. So, relatively easy to interpret are rule-based models. For example, decision trees, they are easy to interpret. The rules provide clear explanations already. They can learn even from little data sets, and the problems with high-dimensional data, with noise and with images, that means ambiguity, okay? And then we have these neurosymbolic models, for example, this or what is deep learning, convolutional neural networks. They are not easy, sometimes even impossible to interpret, and they need a lot of top quality training data. So this is also a very, very important difference. But they can well generalize even from high-dimensional data with noise and is good for images. So summarizing from the very first part, is XA a good name for it? I would say yes. Although misleading, AI or XAI is meanwhile a well-accepted term. Although I also agree that interpretable machine learning would be a better technical term, but XA is broad and this is good, okay? So this slide shows a nice top-level view and shows that XA is a core field and encompasses currently worldwide increasingly important aspects of, for example, fairness, very important, privacy, accountability, transparency, security and safety, and ethics. And this is very important because this is exactly what we need and what we want to achieve, and what is important for the medical domain is ethical, responsible AI. This is a nice paper from the team of Francisco Herrera from Granada, Spain. So the question is XA new, and you have recognized completely correctly that this is a suggestive question and can of course only be answered with no. So David Gunning from the DARPA has coined the term, so explainable artificial intelligence, XA, is first mentioned in the technical report of the Defense Advanced Research Project Agency. But it is just a new name, and for maybe one of the oldest, or it is maybe even the oldest area of AI or of science whatsoever. So what was the most requested feature of early medical decision support systems? So we go now back into the 1970s in the early medical decision support systems. Yes, you guessed it correct again. In the famous work of Shortliff, the most requested feature was the quest for explainability. So explainability was the most requested feature of early medical decision support systems. And you can remember Mycin, we have discussed this last time, was a rule-based system. And of course, these rule-based systems are inherently interpretable. And you see here in this original image from 1975, you have an explanation system. But of course, you know, the main problem was that this Mycin system cannot deal with real-world data because real-world is difficult. But we have discussed this in the previous lecture already. So how did Mycin then enable this explainability? So this flowchart shows how the rule monitor analyzes a rule and decides whether it applies in the clinical situation under each consideration. So each condition is the premise of the rule references and the clinical parameter, and all such conditions must be true for the rule to be accepted. And that is easy to explain, so it's easy to retrace and easy to say why the machine have selected something, okay? So, and this is also possible to ask a system to explain question in retrospect. For example, why did you ask this question, and to confirm the user's decision rules, for example. This was done in plain text, so this is very amazing. And how did Mycin support the why question? So although the why option described above permits Mycin to explain any question that it asks, the system draws, of course, many inferences without requesting information from the physician. And this can happen either because of the preconditions of a rule that were satisfied by deductions, of course, from previous information, or because the needed data had already been requested in the context of a different rule. And thus, even though the physician may understand each question during the causation itself, Mycin's final recommendation might puzzle him and he might want to see them justified. So this is just an part of the original paper of Edward Shortliff. So how was the interactivity for the doctors ensured? So this is an example from an earlier version. This was from 1973. And there was a question answering module which ensured the interactivity. And the medical expert could interactively argument and interact with plain English language. So although Mycin was never accepted by clinicians and was never used in clinical real-world settings, it was groundbreaking at this time for research in AI. And it is now also very important for us and very interesting to see and it was the first expert system ever. So this is very, very important, an important milestone. So what caused the end then of the hype in early AI decision support systems? So this is from an originally abstract of a paper by Randolph Miller in 1982. The evaluation demonstrated that the present form of the program is not sufficiently reliable for clinical applications. And specific deficiency that must be overcome include the program's inability to reason, its inability to construct differential diagnoses spanning multiple areas, its occasional attribution of findings to improper causes, and its inability to explain its thinking. So, although it is considered to be one of the most important milestones in the field of expert systems in computer science at all, it did not achieve the significance in medical applications that had been hoped for. So Mycin achieved very high hit rates in diagnosis, but at the time of its development, the general acceptance of computer systems was very low of the medical doctors, and so was the lack of willingness to rely on the diagnosis of a system that was even difficult to understand, although these are really easier, much easier to understand than our current systems. So a short digression, let us do a short digression. History of decision support systems, DSS, is a history of AI, very short. And the ultra-short history here, the golden years, 1943, Warren McCulloch and Walter Pitts, then 1950, Alan Turing, John McCarthy, then that short-lived Bruce Buchanan with his Mycin, then 1978, Bellman, Can Computer Think, and so on. Then towards the renaissance of AI, so with the success of what we call now deep learning, the quest has come also to explain these black box models. And there was the early work of Judea Pearl embracing causality in default reasoning. And then you can remember the success, for example, the Deep Blue beats Jerry Kasparov, then the successful autonomous driving vehicles, and then IBM Watson Jeopardy. And then in 2016, of course, the huge success of the game of Go by the DeepMind people. So this is very, very interesting. So the last entry is the famous paper by DeepMind. Meanwhile, 7,373 citations. And yeah, very interesting. So what about the history of health informatics? So this is more important for us. Therefore, we will discuss this a little bit in more detail. So because this is for us important in the course Health Informatics. So medical informatics, the classical AI hype. There was the focus on data acquisition, on storage, accounting, and the early expert system. So this is typically medical informatics at this time. And the term medical informatics was first used in 1968, and the first course was set up in 1978, 10 years later. So this is very interesting. And then in 1985, we had this AI winter, and there was a huge hype on health telematics, healthcare networks, telemedicine, CPOA systems. So CPOA is short for computerized physician order entry. So this is a process of electronic entry of a medical practitioner instructions for the treatment of patients. So hospitalized patients, of course, under the care. And then we have the 1995 era, the web era. AI is forgotten. You should not mention at this time the word artificial intelligence. So it is banned from the computer science area. Web-based applications, services, electronic patients records, distributed systems was in the focus. And then 2005, successful statistical learning comes back, so AI renaissance, but it was still not called AI at this time. It was basically machine learning. and also pervasive, ubiquitous computing, Internet of Things. And then 2010, where more and more data was made available, so big data. And big data, you know, is super for machine learning, super for AI. So this accelerated the success in AI. Massive increase of data, but the challenge is here in data integration, data fusion, data mapping, and so on. And then we have today the area of explanation area towards explainable AI. This was fueled to ethical, to social demands, and this means retraceability, replicability, reenactment, explainability, interpretability, sense making, disentangling the underlying concepts, causality, causability, human AI interfaces, and ethical responsible machine learning, trusted AI. This is more or less now state of the art, and this is now the research which becomes more and more important, particularly to go to these human AI interfaces, because somehow the medical doctor must interact with the algorithm, and they are not interested in algorithms per se, they are interested in asking questions to the systems to understand, to learn, and so on. Okay, so quickly the history of health informatics. And why was mycin central for explainable AI in medicine? You see, mycin is a central point here, although in earlier times, so they started with tendril, but mycin still is a very, very important inspiration for many other systems, and we have to emphasize that this was retraceable and thus interpretable by a human expert at this time. So how did the human AI interaction work at this time? So they had tools, expert systems, inference engine, knowledge base, and you see a huge part was the user interface, where they, of course, the interface was a kind of explanatory interface which allowed the interaction between the doctor and the system in plain English language. But this is very good because the medical doctor understands plain language, okay? So this is a really good step to ask these questions in plain language. And find an emulation here from our own group. So there's a Jupyter notebook also here. If you have time, you can look it up and you can see a mycin in action. So what was static knowledge versus dynamic knowledge? So mycin was programmed in Lisp and used judgmental rules with associated elements of uncertainty. So, of course, it was designed to identify bacteria causing severe infections. So, for example, meningitis or bacteremia. And they were designed to recommend antibiotics with the dosage adjusted for the patient's body weight. And Edward Shortleaf was at this time both a physician and a computer science, and he was confronted with problems associated with diagnosing a certain class of brain infection that was an appropriate area for this expert systems research. And this was very important because the first 24 hours are most critical for the patient. And in this slide, we see the idea of the separation of static knowledge here in the upper part of the slide and the dynamic knowledge. And the static knowledge are the rules and facts, and the dynamic knowledge is the entries made by the human. Here you see the consultative advice, explanations, the user interacts, and the deductions were made by the system. So this is the principle of such a rule-based system. So the static were rules and the general facts, the domain knowledge, and the dynamic were the real-time facts entered by the end user, the medical doctor, and the deduction produced by the systems. Please remember here also very important: induction, deduction, abduction. Okay. So what was the shortcoming of the classical logic approach? Because this was a very logic approach, and everybody knows Mr. Spock from Vulcan, from the Starship Enterprise with the pointy ears, and he's a good example for classical logic. We are already well aware about the notion of probable information. And the information available in medicine is often imperfect, imprecise, uncertain. So this is real-world medical science. And human experts can cope with these deficiencies, but classical logic permits only exact reasoning. If A is true, then A is non-false, and if B is false, then B is non-true. And most real-world problems do not provide this exact information. Mostly it's inexact, incomplete, uncertain, or even unmeasurable. And this was the reason why the classical AI approach, at least in the real world, was very unsuccessful at this time. So how did Mycin cope then with these uncertainties? So Shortleaf was of course aware of the problems involved with classic logic, and he introduced was very, very interesting. So to every rule and every entry, he provided a certainty factor, CF, which is between 0 and 1 normalized. And two measures are derived then. The measure of belief and the measure of disbelief. And the certainty factor is then calculated as an element by CF of H, the hypothesis, is measure of belief of the hypothesis minus the measure of disbelief of the hypothesis. And if this certainty factor is positive, then if more evidence is given for hypothesis, otherwise the CF is negative. That means if the certainty factor of an hypothesis H is +1, the hypothesis is 100% true. If CF of H is -1, the hypothesis is 100% false. So this is really very good and was the first of this time. So here an original example from Mycin to make it clear. This is on a later publication from Shortleaf and Buchanan 1984. So here hypothesis 1, hypothesis 2 and hypothesis 3 as an example. And then you have certainty factors. For example, for the hypothesis 1, it is 0.8. So there is strongly suggestive evidence, 0.8, that the identity of organism -1 is Streptococcus. Okay? And the certainty factor H2 is -0.3, so there's weakly suggestive evidence, 0.3, that patient -1 is not febrile. And certainty factor H3 is +1, it is definite that the name of patient is John Jones. So this Mycin example makes the certainty factor, I think, clear. Yeah, why was Mycin no success in clinical routine? This is a funny but actually very serious example why this logic-based systems was not a success. So look it up. If you put just in real nurse triage, you get to such a cartoon movie, and this explains by itself. So what accelerated then the AI renaissance? Yeah, the success came after McCulloch and Pitts, 1943. They rapidly become aware that a single neuron is not enough and that large networks of such elements are required. And so after the perceptron by Minsky and Babbitt, the idea was to use whole networks of perceptrons. And this was then the birth of this, what is now called deep learning. And the problem is now that you have a lot of them. So you have a combination of large networks, and this makes it difficult. So why are large neural networks a problem? So like Richard Feynman said about the universe, it is not complicated, it's just a lot. The big numbers are a huge problem, and you can, of course, believe that no human expert can cope with millions and millions and billions of parameters. And this is the problem. By the way, the paper by Krzyzewski has nearly 62,000 references. So this is one of the very good networks. So this is a famous example. And the famous example should show you the purpose now in the next slide. So to answer the question, why are such black box models now a problem? So here you see the famous example for the success of deep learning. So the group around Sebastian Thrun from Stanford used a deep convolutional neural network as a classification technique. And if we look at the data from left to the right, you see the image of a skin lesion here, for example, melanoma. And this is sequentially warped into a probability distribution over clinical cases of skin disease using a Google Inception V3 CNN architecture. And they pre-trained this with the ImageNet dataset. This is 1.3 million images over 1,000 generic object classes. And the classification results is always communicated as human level, and that is true with 92%. It is really an excellent result, as you can see here. However, what about this 8%? This 8%, we cannot explain where the 8% comes from. Most of all, it is simply not possible to retrace the result, hence to ask the question of why these 8% are wrong. So we ask, what are the underlying explanatory factors which makes this 8% error? And the problem is because of the opaqueness of such a model. Here you see such a model. Although we understand the mathematical principles of such networks, they are just black box models. We cannot peek inside. And such models are now a problem because they are called opaque or black box models, and such models are problematic since May 25th of 2018 because the GDPR came into effect, and now we have a heuristical right for explanation. So this does not mean that we have to explain everything in detail and just in time, so explain everything. No, it is a heuristical right. That means if something happens, then there is the right to ask the question of why. And exactly this is not possible with such approaches. And therefore we need methods which allow this. So what are the two types of black box algorithms then? We can summarize. Success in deep learning resulted in deep problems, for example, complex and exploding gradients. So deep learning methods are representation learning methods with multiple layers of representations, many layers. Problem in our society are also secret algorithms which make important decisions about individuals, but we cannot have insight on it. So this is really a problem. So black box type 1 is too complicated for a human to understand, and black box type 2 is proprietary. That means the secret algorithm. So this is both a problem. Yeah. So which two top-level explainable AI methodologies do we have then? So we have this post-hoc. Post-hoc comes from Latin, after this event. So such approaches provide an explanation for a specific solution of a black box approach. These are the upcoming Lime, Beta, LRP. And then we have Ante-hoc. This means before this event. So such methods can be human interpreted immanently in the system. So they are transparent by nature. They are also called therefore glass box approaches, similar to the interactive machine learning model. Yeah. So they are per se interpretability. And unfortunately, the best performing methods to date are these black box models. So maybe in the future, there's a possible combination of deep learning with graphs, for example, with knowledge graphs in form of ontologies. So this is just an idea how we can deal with it in the future. So examples for Ante-hoc models, interpretable machine learning, very briefly. Again, Ante-hoc before this event. So these systems are inherently transparent by nature, glass box. And here I have to note that many Ante-hoc approaches appear to be to the new student particularly novel, but these have a long tradition and were used since the early beginning of AI and applied in expert systems, as we have seen before. So typically decision trees go back to ancient Greeks, for example, or linear regression or random forests, very old models. So a typical example, and you know already that graphs are extremely versatile from the last lecture, and here we see how they support explainability. Here you see an action influence graph. This is from a StarGraph 2 agent with exogenous variables hidden. So these action influence models are structural causal models, except that each edge is associated with an action. So in the action influence model, each state variable has a set of structural equations. So one for each unique incoming action. And in this example, the variable a index n, so a sub n, is causally influenced by s and b only when action a sub m is executed. So this is a very interesting approach, explainable reinforcement learning, and this is powered by graphs. You see how powerful graphs are. So another example are stochastic and/or graphs. This is in form of trees. Remember, decision trees have been used in medicine for a long time. And here we see a typical stochastic and/or tree. And you can, for example, get explanations backwards here from the categories. So each terminal node here is associated with a geometric OR node, which accounts for its deformation and articulation. Okay, and final example, Bayesian rule lists, BRL, they produce a posterior distribution over permutations of if-then rules, starting from a large pre-mined set of possible rules, and the decision lists then with high posterior probability tend to be both accurate and interpretable at the same time, where the interpretability comes from a hierarchical prior over permutation of rules. So this is a nice example by Latham and Cynthia Rudin, and this is on clinical prediction rules for estimating the risk of stroke in patients with non-rheumatic atrial fibrillation. This is this AF, and this is a called CHATS score, and the updated version CHATS 2, for example. This is a clinical prediction. So it's a very good example. Okay, examples for post-hoc model. So post-hoc, after this event, so such approaches provide an explanation for a specific solution of such a black box approach. And the caveat, post-hoc explanation can be misleading. So also from Cynthia Rudin, so nice paper, you should read that. But if it would be that easy what Cynthia is proposing, so this is really not so easy. Yeah, stop explaining black box machine learning models for high-stake decision and use interpretable models instead. Often, sometimes, deep learning is really cool and can achieve things which we cannot achieve with others. So, yeah. So what are typical post-hoc approaches? There are a lot of different approaches. The easiest one is gradient. You know from your school time, gradient is a multivariable generalization of the derivative. Then we have sensitivity analysis as a basic instrument. So perturb a model and look how robust the system responds. So testing for robustness. Then we have decomposition. And here a famous proverb from Jan LeCun is the world is compositional. So if it is compositional, you can decompose it. For example, typically into pixels or layers or deep Taylor decompositions. And then we have optimization methods. That means select the best element which contributed to the output. Lime, for example, or beta is such a method. Then we have deconvolution and guided backpropagation. That means reverse the effects of convolution, therefore deconvolution. Brings out from two functions a third function, which is the product of both. It's very cool. And there's model understanding. So understanding the model means looking for human interpretable models, debugging deep learning models, for example, via feature visualization or inverting CNNs, or this qualitative testing with concept activation vectors, which we will get to know at the end of this lecture. And then, of course, network dissection. So let's start with LIME, because it was among the first models of this explainable AI stuff, and it is agnostic. So agnostic means something, a model, a process, or anything that is generalized so that it is interpretable among various systems. And the word agnostic comes from Greek, a meaning without, and gnosis meaning knowledge, without knowledge. So in IT, that translates to the ability of something to function without knowing the underlying details of a system that it is working within. As with interpretability, agnosticism is typically enabled for either compliance with widely used standards or added elements such as coding that will enable one system to function in a variety of information environments. Okay, what is the general principle of LIME? So here you see the nice picture from the original paper. This was the first paper, so this was the PhD work of Marco Tullio Ribeiro. So why should I trust you? Explaining the prediction of any classifier. So explaining individual prediction. A model predicts that the patient has flu, for example, here, and LIME highlights now the symptoms in the patient's history that led to the prediction. Sneeze, headache are portrayed as contributing to this flu prediction, while no fatigue is evidence against it. With this, a doctor can make an informed decision about whether to trust the model's prediction or not. So it is clear that the doctor is much better positioned to make a decision with the help of such a model if intelligible explanations are provided. In this case, an explanation is a small list of symptoms with relative weights, and symptoms that either contribute to the prediction, that is in green, for example, here, or are evidenced against it in red. So humans, and I have to emphasize that humans have usually a prior knowledge about the application domain, which they can use to accept and therefore trust or reject a prediction if they understand the reasoning behind it. So it has been observed, for example, that providing explanations can increase the acceptance of recommendations of automated systems. So this is really very important. Okay, so what are explanations in the sense of LIME? Yeah, explanation here is a local linear approximation of the model's behavior. So while the model may be very complex globally, it is easier to approximate it around the vicinity of a particular instance. And look at this image. The model's decision function is represented by the blue-pink background here. And this is clearly very difficult, highly non-linear. And the bright red cross is the instance being explained. So let's call it X, for example. And we sample now instances around this X and weight them according to their proximity to X. So the weight is here indicated by the size of these balls and these crosses. And we learn a linear model, this is the dashed line here, that approximates the model well in the vicinity of X, but not necessarily globally, of course. So therefore local interpretable, okay? And yeah, this is the algorithm of this. So this is the original algorithm. So this produces an explanation for an individual prediction. And the complexity does not depend on the size of the data set, but instead on time to compute f of x and on the number of samples n. So in practice, explaining random forests with 1,000 trees using scikit-learn on a laptop with n of 5,000 takes under 3 seconds without any optimization, such as using GPUs or parallelization. So this is quite doable. So it's quite a nice approach. Okay, how is the explanation produced by this LIME? So formally, Marco defined an explanation as a model small g element of capital G, so small g element of capital G, where the capital G is a class of potentially interpretable models. So for example, these linear models or decision trees or rule lists and so on. And he has then following rule lists, classification models consisting of an ordered list of if-then rules, where the order of rules determines which example should be classified by each rule. And this is very important by healthcare applications where patients would be stratified. Remember, personalized, stratified, generalized. So into risk sets, for example, and the highest at-risk patients then should be considered first. And this can easily be highlighted by a Bayesian framework for learning these following rule lists. So the model small g element of capital G can be presented to the user with visual or textual artifacts, and the domain of small g acts over absence presence of the interpretable components. So as not every g element of G may be simple enough to be interpretable, so we have this omega here, this large omega of G, function of G, as a measure of complexity. This is called complexity score for this interpretability, and as opposed to this fidelity score. So this is the distance matrix here in the feature space, the pi of x z. Okay, this is a typical LIME examples, and there are meanwhile hundreds of working examples and many applications examples. So this is really relatively widely used, and this is a typical example. Yeah, and this is a nice example. So there's an own book on it from O'Reilly about this LIME. You can look at this and you can play around with it. So this is a further example here. So explanation for a prediction from the inception. The top 3 predicted classes are here: the tree frog, the pool table, and the balloon. Yeah, just to play around. Yeah, what are the LIME pros and cons? Very popular, many applications, contributors, model agnostic, as we have learned. Minus is local model behavior can be unrealistic, of course. Unclear coverage and ambiguity. How to select the kernel width. This is a big problem with it. But LIME is one of the most popular libraries with over 5,000 stars on GitHub. So it's really very cool. So remember, there are myriads of classifiers. So a hierarchical classifier is a classifier that maps input data into defined subsumptive output categories. And this is just to make you aware that there are a lot of different classifiers. So this is in machine learning and statistics, classification is the problem of identifying to which of a set of categories, that means subpopulations and new observation, belong, and on the basis of a training set. Okay, what is the difference to the follow-up? There's a follow-up work and modification where the same authors introduce a further model agnostic system. This is from 2018. And this model agnostic system explains the behavior of complex model with high precision rules called anchors, therefore anchor. Yeah, and these anchors represent local sufficient conditions for predictions. The algorithm here computes these explanations for any black box model with high probability guarantees. So an interesting extension is the visual question answering, VQA, where you can ask questions. For example, where is the dog? And the answer is then the dog is on the floor. But I emphasize that this is work in progress and this is absolutely not trivial. So visual question answering is a task that has received immense consideration from two major research community, from computer vision and of course from natural language processing. So, and recently it has been widely accepted as an AI complete task, which can be used as an alternative to the visual Turing test. So, you know, in its most common form, it is a multimodal challenging task where a computer is required to provide the correct answer for a natural language question asked about an input image. So this is by far not trivial. But of course, it attracts many deep learning researchers after their remarkable achievements in text, voice, and vision technologies, of course. Yeah, but this is difficult. I just mentioned it. Yeah, and of course there's a very recent work on graphs, graph-lime chord. So in the last lecture you can remember the versatility of graphs. Here a very recent example. So the equation here shows how to obtain the explanation. So given a GNN model f, the node nu is being explained, and the sampling local information matrix x sub n of v and an interpretable explanation model G. So the explanations for the explained nu here, or v. Yeah, v. So zeta is this Greek letter zeta of v is then the set of features as explanations of the node being explained. And on the left side here, the algorithm where they summarize the model agnostic and nonlinear explanation framework based on N-hop network, here the N-hop network, sampling, and lasso for GNS as a procedure, which they call then graph-lime. So lasso, if you don't have heard it, the lasso is a special lasso here called Hilbert-Schmidt Independence Criterion lasso, ASIC lasso. For lasso, generally, you can refer to regression, shrinkage, and selection via the lasso. The classical paper is by Rob Dibshirani, which has amazing 33,354 citations today. It's very amazing. So let's proceed with beta, black box explanation through transparent approximation. So this is a classical work, beta. Is a model agnostic approach to explain the behavior of also an arbitrary black box classifier. And interpretability and accuracy at the same time are difficult to achieve. We have already heard that. And consequently, users are interactively integrated into the model and can thus explore the areas of black box model that interest them most. So this is a typical human in the loop approach, and this gains enormous interest because the human has a very good understanding of, because he has a lot of previous knowledge and has this contextual understanding which is missing in artificial systems. So this is quite good. So how does beta or beta look like? So remember, agnostic means that the learning algorithm has no a priori knowledge of the classification. So let us look at the algorithm. So here you see, while exactly solving the optimization problem here in equation 1 is NP hard, the specific properties of the problem is non-monotonicity, submodularity, non-normality, non-negativity, and this can be done here and provide an unprovable optimality guarantee. So what are the measures of fidelity, interpretability, and unambiguity? So these are with regard to a two-level decision set, approximation set R, a black box model B, and a data set D, where X sub I captures the features values of instance I, and this black box model B is treated as a function which takes an instant X element D as input and returns a class label. So the definitions are given on the next slide. Do you see this here? The definitions of the original paper. And this is very easy to see by yourself. So this is from a further paper presented at the ACM SIG KDD. And on the left you see a beta example, and on the right, so in the left here, this is the beta example, and on the right this is a decision list. And these are more comprehensible to humans because rules apply independently. So you can have a look at the GitHub repository of Himabindu. So what are beta pros and cons? It's model agnostic, learns a compact two-level decision set, is unambiguously, but it's not so popular, interestingly, and has not so many libraries, unclear coverage, and needs care. And this is therefore not so much used in the community. Very popular now is, maybe one of the most popular XI methods is LRP. So this is from the TU Berlin group around Klaus Robert Müller. And on layer-wise relevance propagation you will get our last assignment. So how can we describe LRP at a glance? So it is a general solution for understanding classification decisions by pixel or layer by layer, hence the name, decomposition of nonlinear classifiers. And this is done in a highly simplified way. That means LRP allows to go backward through the thinking processes of neural networks. And thereby it becomes comprehensible for a human which input had which influence on the respective result. And in individual cases, how the neural network came to a classification result, that means which input contributed most to the gained output. And this is a good example. If genetic data is entered into a network, it is not only possible to analyze the probability of a patient having a certain genetic disease, but with LRP also you can see the characteristics of the decision. And such an approach is a step towards personalized medicine. Remember the concept of personalized medicine, to provide an individual cancer therapy that is tailored to the particular individual patient. So how does the LRP work in principle? So no lecture without a cat. Here your cat image. So the cat image is converted to feature vector representations. Then a classifier is applied to assign the image of a given category. So cat or no cat here, red cat, no cat blue. And the method then decomposes the classification output f of x into sums of feature and pixel relevance scores. And these are the relevance scores R index E or R sub E. And the final relevances are visualized and contribute and visualize the contributions of each single pixels to the predictions. This can be seen here. So the input image is processed by the network. This is the network output, and the output value is back projected. You can see this here, layer-wise, back projected into pixel relevance value R index F, and this can be visualized by a heat map then, and this can be seen here. So the heat map then shows which contributed most to the result. So this was the famous work by Sebastian Bach, and this is not the Sebastian Bach the musician, this is Sebastian Bach from the TU Berlin. And note that Sebastian Bach is married and adopted the name of his wife, and he is now called Sebastian Labushkin. Just as a side note. Okay. So how does a neural network classifier during prediction time look like? This is beautifully here in detail. So on the left, a neural network shaped classifier during prediction time. So W sub ij are the connection weights, and a subscript I is the activation of a neuron sub I. And write the neural network shaped classifier during layer-wise relevance computation time. So R subscript E, index E is the relevance of neuron sub I, which is to be computed. So in order to facilitate the computation of R subscript I index I, they introduced messages called capital R index. This is the relevance score. And you can see this here. So these are messages which need to be computed such that the layer-wise relevance in the equation below is conserved, or let's say satisfied. Satisfied is maybe the better term. So the messages are sent from a neuron sub I to its input neuron S sub J via the connections used for classification. For example, 2 is an input neuron for neuron 4, and 5, 6, neuron 3 is then an input value for 5 and 6, and neurons 4, 5 and 6 are input for neuron 7, and so on. And this can be then really neatly depicted with a heat map. So this is a little bit, let's say, in advance, because we will later on get to know about Taylor decomposition. So this is quite interesting because it was mentioned in the work of 2015. And this is an example for a real-valued prediction function for classification with the dashed black line. Here you see the dashed black line being the decision boundary, which separates the blue here from the green dots. And the blue dots are labeled negatively and the green dots are labeled positively. Okay? And that means on the left hand you see the local gradient of the classification function at the prediction point. And on the right you see a Taylor approximation relative to a root point on the decision boundary. And you see, tricky is to find the root point. So the figure is a nice depiction of the intuition that a gradient at the prediction point x, and here indicated by the square, does not necessarily point to a close point on the decision boundary. So instead it may point to a local optimum or to a faraway point on the decision boundary. And you see in this example the explanation vector from the local gradient at the prediction point x has a too large contribution in an irrelevant direction. So the closest neighbors of the other class can be found at a very different angle. Yeah, and thus the local gradient at the prediction point x may not be a good explanation for the contributions of single dimension of the function value f of x. So this is quite a nice example. So what is then the output of the LRP? Here we see the LRP pipeline and the computed heat map. Note that it goes into the reverse direction. So heat mapping is an important ingredient of knowledge discovery and exploratory analysis and understanding of complex data in the science, but also in industry and beyond the presented field of image analysis here. And of course in medicine. So no lecture with a cat. Here's your cat. And a further example for such a heat map. It shows the pixel-wise decomposition of bag of words features over a histogram intersection kernel using LRP for all subsequent layers and rank mapping for mapping local features. So each triplet of the image shows from left to right the original image, the pixel-wise predictions superimposed with prominent edges from the input image and the original image superimposed with binarized pixel-wise predictions. Okay, what is relevant in a text document? So here we see a diagram of a CNN-based interpreted machine learning systems for applied to text, so language. So it consists of a forward processing that computes for each input document a high-level concept, for example, a semantic category or sentiment, and a redistribution procedure that explains the prediction in terms of words. So, you know, text documents, the cat sat on the mat, can be described by a number of abstract concepts such as the semantic category, the writing style, or sentiment. And machine learning models have been trained to automatically map documents to these abstract concepts, allowing to annotate very large text collection. And this is a good example for making it also interpretable. And this shows then, we see this on the next slide, this shows then what is relevant in a text document in a certain context. Okay, so here the PCA projection of the summary vectors of these newsgroups text documents, yeah. And the LRP SA-based weightings were computed using the ML model's predicted class. The colors here denote the true labels. So what you see here is that this LRP method provides semantically more meaningful semantic extraction than baseline methods. So now we continue with deep Taylor decomposition. Note all these methods are working because of what Yann LeCun always says, the world is compositional. So what are Taylor series? From our college time we know Brooke Taylor from Edmonton in England, not the Edmonton in Alberta. So there is an excellent video about Taylor series made by Grant Sanderson. I highly recommend that you look at this really well done animation. So Taylor functions, Taylor series of a function is an infinite sum of terms, you see this here, expressed in terms of the function derivatives at a single point. So for most common functions, the function and the sum of its Taylor series are equal near this point. So you can also refer to some more information about this. So what is then Taylor decomposition at a glance? So there's an excellent introduction to deep Taylor decomposition by the Berlin machine learning group around Klaus Robert Müller and Wojciech Samek from Fraunhofer in Germany. And a possible explanation here can be obtained by determining which input variables, here pixels for example, have contributed to the image classification. In particular, what pixels in the image are relevant for the prediction outcome, as we have learned before. We call an assignment of scores onto pixels the heat map. And such heat map can be then visualized as an image of same size as the image to classify. And in the heat map, you see this here, relevant portions of the image are highlighted in red, for example, in red here. And the contour here is a shark, not a cat, it's a shark. The shark maybe eats the cat. And the shark and its dorsal fin are considered relevant. Here, this fin is relevant for the classification. So the machine learning model is therefore an opening of the black box. So this is running a backward pass on the neural network. Very good. So why must the heat map be conservative, positive and consistent? Because we would like to associate to each pixel p in the image a relevance score, Rp of x. And that indicates for an image x to what extent the pixel p contributes to explaining the classification decisions f of x and to store the relevance for each pixel in the heat map. So the heat map must satisfy the following properties, the three requirements, conservative, positive and consistent, as based in this, or as you can see in these definitions. So what about sensitivity analysis versus decomposition? This is a nice slide. So the colleagues here make a distinction between the following two questions. For example, what makes the cat less or more cat, or what makes the cat a cat? And this is a subtle difference. So the second question, what makes the cat a cat, is better answered by decomposition techniques. So a decomposition here seeks to redistribute the whole predicted output onto input pixels. And therefore decomposition technique seeks to explain the prediction in its entirety rather than only measuring a differential effect. So here in this slide you see we see the difference between sensitivity here and decomposition by looking at a simple two-dimensional example, a sum of two nonlinear functions, each operating on one variable of the input space. So the function value here is represented with contour lines, and explanations are represented as a vector field. Yeah, and how is the computational flow of deep Taylor decomposition in more detail? Here we have the cat again. So this is a beautiful illustration of the Berlin group on how it works in detail. So the computational flow of a deep Taylor decomposition, a prediction for the class cat, is obtained by forward propagation of the pixel values x of index p here, and is encoded by the output neuron xf. And the output neuron is assigned a relevance score. R of f is xf, representing the total evidence for the class cat. And now the relevance is back propagated from the top layer down to the input, where Rp denotes the pixel-wise relevance scores that can be visualized again as a heat map. And then you see what contributes here to a cat classification. So how does the relevance redistribution work? On the left hand you can see a 3-layer deep network composed of increasingly high-level feature extractors, and right you see the diagram of the two proposed relevance models for redistributing relevance onto lower layers. So the upper layer relevance is not only determined by input neuron activations of the considered layer, but also by high-level information. That means abstractions, and that have been formed in the top layers of the network. These high-level abstractions are necessary to ensure the global cohesion between low-level parts of the heat map. Okay, so this is just an example. So images of different classes: frog, here we have frogs, sharks, cat, sheep. And this is given as input to a deep network and displayed next to the corresponding heat maps. And the heat map scores are summed over all color channels of the image. Okay, the example from histopathology, we have seen this before. So at first we need to define what we want to have to explain, what and to whom and in which way. And this is central in the medical domain for medical diagnosis. Also, but it's also relevant for us engineers. Do we want a mechanistic understanding or functional understanding? So you have to start. Yeah, and here we have again this tumor infiltrating lymphocytes, short TAEIL, evaluation. So from left, the original agent A breast cancer. So agent A short for hematoxylin and eosin. And here you see then the regions with respect to the lymphocyte. So green is no lymphocyte, red is high content of lymphocyte. So the heat map explains the classifier decisions with pixel-wise resolution. And yeah, this is very, very relevant for the medical domain. So here, finally, a recent example. So the paper is from April 2020. So agent E, you know, is short for hematoxylin and eosin. So here in A, you see exemplary visual explanations superimposed on grayscaled agent A stain. And for these three studied tumor entities, red denotes the positive relevance, for example, in favor of the prediction of class cancer, while blue denotes negative relevance, so here contradicting the prediction of class cancer. And corresponding annotations can also be found here. And this is really a very good example for layer-wise relevance propagation. But please remember what we said. The next step is this understanding, this human AI interface. This is the technical explanation. So the next step is to make it really explainable to or interpretable to the human. And therefore I think interpretable is a better term. Okay, a further interesting method is prediction difference analysis. This is a very basic method. So the this work of relevance measures go back to a relatively old work by Marko Robnik and Igor Kononenko from the University of Ljubljana. So the basic idea was for a given prediction, the method assigns a relevant value to each input feature with respect to a class C. And that means that relevance of a feature x index I or x sub I can be estimated by measuring how the prediction changes if the feature is unknown. That means the difference between P of C given C jx here is and B C x y is the evaluation of the prediction when the feature is unknown. So here it is first to label the feature as unknown, and which only few classifiers allow. So which only, yeah, of course. And the second is to retrain the classifier with the feature. So we will see the practical implementation on the next slide. So here you see the algorithm, so sample illustration here of the procedure in algorithm 1 here. Given the input image X, we select every possible batch XW in a sliding window fashion of size K times K and place a larger patch of X of W, index W here of size X around it. And then we can conditionally sample XY, XW by conditioning on the surrounding batch X sub W. So although this paper, this super pixel-based prediction difference analysis sounds so nice, and I have read it with great enthusiasm, this paper received so far no citations. So it's an interesting or at least theoretical approach, because I couldn't find anything implemented to play around. So, but it was nice, this super pixel-based prediction difference. So the input image here, the input image, this is the original input image here, this bird with classification results. This is here a macaw with confidence 0.9. And here we have the superpixel, so the prediction difference analysis with this superpixel, and then the resulting map visualize what contributed most. So the resulting map visualizes the supportive, this is here the red, versus unsupportive blue likelihood. This is the significance score of the components toward the classification. But this just for the sake of completeness. Okay, a digression, visualizing CNN with deconvolution. Let us do briefly some deep learning archaeology. This is from the early days. So our typical example to answer the question of why. You can surely remember now this famous example. We have discussed this several times. The first who thought about how to get insight into such a network have been Seiler and Fergus. And on the next, you see this classification technique is a deep CNN. Data flows from left to right. The image of a skin lesion, for example, melanoma, is sequentially warped into the probability distribution over these clinical cases. You know this from previous. And now, this is the famous work of Matt Seiler and Rob Fergus from 2013. So actually this is the beginning of the successful time of deep learning. So this is deep learning archaeology actually. And this paper was first on arXiv and 1 year later presented at the European Conference on Computer Vision and has meanwhile 9,000 citations. So the idea is quite simple and fantastic. So the deconfnet layer left is attached to a confnet layer right, and the deconfnet will reconstruct an approximate version of the confnet features from the layer beneath. So this provides a continuous path back to image pixels. So this is quite an interesting approach. And So here we see more detail, the process in more detail. So below the colored here, so unpooling in the ConfNet, the max pooling operation is non-invertible, but we can obtain an approximate inverse by recording the locations of the maxima within each pooling region in a set of switch variables. So in the dconfnet, the unpooling operation uses these switches to place the reconstruction from the layer above into approximate locations, preserving the structure of the stimulus. So on top we see the full architecture of the 8-layer ConfNet. So the 224 to 224 crop of an image, this is this one, with 3 color planes is presented as the input. And this is convolved with 96 different first layer filters. This is red. And each size 7 by 7 using a stride of 2 in both X and Y. And the resulting feature maps are then passed through a rectified linear function. This is not shown in this image. And pooled maximum within 3 times 3 regions using stride 2 and contrast normalized across the feature maps to give 96 different 55 times 55 element feature maps. So the last 2 layers then are fully connected and taking features from the top convolutional layer as input in vector form. This is again 6 times 6 times 256, meaning 9,216 dimensions. So this is quite an interesting approach. And you see here the visualization of features in a fully trained model. So for layers 2 to 5, we show the top 9 activations in a random subset of the feature maps across the validation data. And yeah, this is quite interesting what such a network learns and sees. And here, a further proof to answer the question, is the world compositional? Yes, obviously, but because otherwise, this is exactly what Jan LeCun always emphasizes, the world is compositional and therefore these networks are working. And we have a chance to understand it step by step, layer by layer, it can be visualized. One problem is that it rapidly becomes so much that due to the complexity we cannot understand it then. So we have now a lot of variant methods, for example inverting GNS, guided backpropagation, deep generator networks, but for this introduction lecture we will now continue with one final method. This is testing with concept activation vectors, TCAV. And if I would say that, my students do not believe it, therefore luckily Pichai Sundarayan, this is really good that Sundar Picharayan is the CIO of Alphabet, and when he is saying it I can point and reference to him. So he says it's not enough to know if a model works, we need to know how it works. And on the Google keynote exactly 1 year ago, Sundar emphasized the importance of the field of explainability, interpretability, and this is excellent for us because now I can say Google is doing it. And we do what Google does, and therefore it must be good. And he also provided a perfect example, a really perfect example, bias. For example, here on this slide, and you can look this keynote via YouTube, and I would recommend to do so. So here you see a white coat, a stethoscope, and male are the concepts for a doctor. So you can guess now DCAV is a Google initiative. So testing with concept activation vectors is an interpretability initiative from the Google AI team. and we will go for it now. Okay, at a glance, let us quickly rehearse some facts before going into more detail. So, machine learning models work on low-level features. We know that already. Edges, dots, lines, pixels, circles. But we know also that humans are working on high-level concepts like shape, size, color, Gestalt principles and so on. So every pixel of an image is an input feature and are just numbers which do not make sense to humans. So TCAV enables to provide an explanation that is generally true for a class of interest beyond one image. So this is really to go for a global explanation. So the goal of TCAV is a high one. It is to learn concepts from examples. So this is really a cool idea. So it is TCAV, for example, needs a couple of examples of female and something not female to learn a gender concept, for example. Okay, how does a concept activation vector work? So interpretability methods like saliency maps use the gradients of logit values with respect to individual input features like the pixels and the compute and the partial delta h. Delta h sub k of x over partial delta x sub a and b. And then the first partial derivative of x with respect to x is equal to dx over dx. And below we can see then the overall, let's say the overall formula for achieving this. So by using the CAVs and the directional derivatives, we gauge the sensitivity of machine learning predictions. So this is to measure the sensitivity of model predictions. And here we can say, and this is why we have this brain here, that there are functional similarities between neural networks and our brain. So what they have in common for sure is that in each layer the representations become more and more abstract and concepts emerge in the context of learning. So this is very interesting, and by looking for examples, circuits and weights are produced. And this is the deviation can be recorded via loss function and then gradually improved via backpropagation. So this is really a cool concept and the similarity. So here look at testing with concept activation vectors. So given a user-defined set of examples and random examples, for example labeled data of here this class zebras. These are zebras, different zebras. And you have a trained network C, and TCAV can then quantify the model sensitivity to the concept for that class zebra here. And CAVs are learned by training a linear classifier to distinguish between the activations produced by concept examples and the examples in any layer D. So basically the CAV is a vector orthogonal to the classification boundary. This is the red arrow here. You can see this. So for the class of interest, the zebras, TCAV uses the directional derivative to quantify the conceptual sensitivity E. Okay, that is how it works. And how can TCAV applied in the medical domain? So here a good example. This is from retinopathology, and this is green. Green is the domain experts label on concepts belong to the level, and red is the domain experts label of concepts does not belong to the level. And this is a real-world example and shows that the model is inconsistent with doctors' knowledge of classes when the model is less accurate, for example. So, for the sake of completeness, we shall briefly mention sensitivity analysis, because I have mentioned this quite often now. So your question is of course absolutely correct if you say, what is sensitivity analysis? So there is a nice work from Andrea Sardelli et al. From 2004, sensitivity analysis in practice. And sensitivity analysis is the study of how the uncertainty in the output of a mathematical model or system, that can be numerical or elsewhere, or otherwise can be divided and allocated to different sources of uncertainty in its inputs. So, sensitivity analysis is a classic, versatile and broad field with long tradition and can be used for a variety of different purposes, including robustness testing, and this is very, very important for machine learning now. So, robustness is I would say the most sought issue. And then understanding the relationship between input and output. And this is exactly what we want. So a related practice in an uncertainty analysis has a greater focus on uncertainty quantification and propagation of uncertainty. So ideally, uncertainty and sensitivity analysis should be run in tandem. Now this would be ideal. So you can use this for studying and reducing uncertainty. And you can remember how important this is for decision making under uncertainty. So, many methods in machine learning seem to be new, but many are really very, very old. So this is just an slide for you, for your convenience. So an overview is given by the excellent book of Goodfellow and Bengio and Courville. So, for example, chain rule, for me, amazing that this was invented by Leibniz 1676 and L'Hopital 1696. Calculus algebra, of course, and then gradient descent was introduced by Cauchy 1847. Gradient descent, what you think is novel, is invented by Cauchy 1847. And this was used to fuel machine learning in the 1940s. Perceptron, for example, but was limited to linear function. And therefore, learning nonlinear function required the development of a multi-layer perceptron and methods to compute the gradient through such a model. And this was then elaborated by Lecan in 1985, Barker, Rumelhart, Hinton, and so on. And you know, this was then the success story of deep learning. So, what are saliency maps? I have to first to explain it in simple words. So, this is an image that shows each pixel's unique quality. So, it's a quality measurement. So, the goal of a saliency map is to simplify or to change the representation of an image into something that is more meaningful and easier to analyze for a human. For example, if a pixel has a high gray level or other unique color in a color image, that pixel's quality will show in the saliency map and in an understandable way. So salience is a kind of image segmentation, you can say, segmenting. And salience estimation may be viewed as an instance of image segmentation. You can see this beautifully. And why I'm showing you this is that this image below is also a really nice example for on how a neural network learns from a compositional world, and maybe our human brain works similar. So this is very, very a nice picture. And this saliency map can be used for sanity checks. So sanity check in German is Plausibilitätsprüfung, and this is very important in the medical domain. Okay, so what are saliency maps again? So in computer vision, you see a saliency map is an image that shows each pixel unique quality. We have seen that. And why I'm showing this is a very old paper from Morch from 1995. This is one of the first papers on this. And here you see some examples with weakly supervised object segmentation using some ConvNets with. This is from Karen Simonian, Andrea Vitaldi, and Andrew Zisserman. So this work, by the way, was an output of the ERC grant WISREC. This is a very interesting project. Okay, what is the main principle of sensitivity analysis? So we have a function, a data point x, and the prediction f of x1 to xt. Now the sensitivity analysis measures the local variation of the function along each input dimension. So this is the partial derivative of f of x over x sub I, and this squared. And with other words, SA produces local explanations for the prediction of a differentiable function f using the squared norm. This is the squared norm of its gradients with regard to the inputs x. And then the salience map as produced with this method describes the extent to which variations in the input would produce a change in the outputs, and this is this expression. Okay, what do we want to know? So I would say this is the final slide now. So I would say this is enough for now. Of course, there are a lot of other methods, but we have now a good first solid understanding so that you are now well prepared for your third and last assignment. So what do we want to know? So given an image classification, we aim to answer two questions. What does a class model look like and what makes an image belong to a class? And to this end, we visualize canonical images of a class and class saliency map for given image and class. And both visualizations are based on the class core derivative with regard to the input image. This is computed using the famous backpropagation. Okay, for this I would say it's really now enough. You are now well prepared for your third and last assignment. And I wish you to stay healthy and wish you a wonderful time and enjoy the evening or whatever you do now. So thank you very much for listening and